मेरा ख्याल है कि हम अभी कर लेते हैं क्योंकि ये लोड होने में भी ना 130 पे मैम 130 पे सर को लाइव ले लेते हैं बस ठीक है। हाँ 130 हो गई बस हो गया स्टार्ट कर म्यूट प्रेस्ड
So are we ready now? Can we start now?
Yes, sir. We can start definitely. So, okay, ladies and gentlemen, let's begin with the lecture 3 of our course series on applied biomedical AI. And we have around more than 304 participants in person, online through Zoom. And we will also be having participants joining us in person in COMSTECH as well. So with this, I would request Professor Dr. Chen to begin his lecture number 3 of this certificate course, that is Supervised Machine Learning Method, Part 1. So, sir, over to you for the lecture, please.
Okay. So today is the third lecture. Now, from today, we are going to look at individual AI method and beginning with the simpler ones, particularly supervised machine learning method. Today, we are going to focus on 3 sets of methods. The first set is actually very, very simple supervised machine learning method. And essentially, we try to answer this question: how can we generate remember the linear equation, the straight line that separates positive and negative samples, or positive negative data. Okay. The second is essentially a unique method because frequently we are dealing with nonlinear, non-simple type of borderline that separates the samples. And what can we do with this nonlinear distribution of the borderlines? Essentially, there's a very simple method that actually views the borderline from the perspective of the samples. So this is called the K nearest neighbor method. It's very unique, very algorithm-wise, it's very simple, but capability-wise, it's very useful for nonlinear type of borderline. Actually, any kind of nonlinear borderline is supposed to be able to handle. But of course, there's a catch. We're going to talk about it later on. The third method is Bayesian method. Based on the name, we know that it arises from a very famous mathematician. So this method is essentially a statistical method. So we are going to touch the heart of statistics. So we use these 3 sets of methods to illustrate a simpler machine. So illustrate a machine learning method, a supervised machine method. Of course, there are some more sophisticated method which will be the topic of the next lecture. Okay. Now about the simple ones. Okay. Remember that we want to determine the equation of the linear equation of the borderline. So here in the figure, you see this figure, you see the examples of the samples, red one being the positive and the blue one being the negative. And we can imagine there is a borderline which separates the pink region from the light blue region, right? So the question is, how can we determine the linear equation of this borderline? Okay, so essentially, this particular method we are going to discuss is so-called nearest mean classifier. Okay, so in this method, of course, we are given a training set of red dots plus the blue dots, right? So red being the positive, meaning that they are cancer, they are from cancer patients, okay? And then the blue ones being the essentially it's kind of essentially it's not really a serious cancer, but rather it's a benign type of tumor, so it's not really harmful to a person. So in order to be able to determine the borderline, so the first thing we have to do is to focus on the red ones, the cancer ones, okay? So we can easily calculate the average value of all those red dots, right? The average position, which is indicated by the yellow star. You see that is the position of the average position of all the red dots, okay? Likewise, we can also calculate the average position of the blue dots, which is indicated by the green star below, green star here, so yellow star here, green star here. Okay. So once these two positions are determined, okay, so the borderline can be easily determined in such a way that we start with any samples. For instance, we start with these samples. We can calculate the distance between this sample and the yellow star and this star sample with the green star. Of course, we are going to have a shorter distance, either the distance with the yellow star in this particular case, and the longer distance with the green star. And in this case, we can color the position with the pink color simply by the actually by the fact that it's closer to the yellow star, and then we can start with any position, and then any position here or there, and then we can calculate the distance to the yellow and to the green star, and then color the position based on the which star it is closer to. In this way, we can easily arrive at this situation that we have a zone of the pink region and a zone of the light blue region. In this case, the borderline is just a naturally formed by the interface between these two zones. So this is one method to determine the borderline of the positive and the negative samples. We do notice that in this particular example, the borderline is not perfect because we can see there's one blue dot in the pink zone and two red dots in the light blue zone. So this is called the error. That's, of course, we know that when we train a machine learning or deep learning method, actually the machine learning model or deep learning model actually comes with a certain level of error. So this is one example of the error because of the the inability of the model to really model this complex borderline problem, because after all, we use a simple borderline to separate the positive and the negative samples. Now we look at the second so essentially it's the same method, but rather it's just repeat the steps of how you can determine the borderline. Okay, so now we look at the next one. Okay, in next slide we are going to talk about the second simple machine learning method. Is called the Fisher linear discriminant method. Okay, in this particular example, again we have a distribution of red dots and blue dots. Okay, so the question is how we determine the borderline. Okay, so we can simply draw any straight line on this particular space. For instance, we draw this green line. Okay, and then we can once we draw this green line, any one is okay in any orientation, any position. That's fine. Okay, we can simply project all the red and the blue dots onto the line, and you can see the mixed distribution of the red dots and the red dots. Okay, so this is a one particular possible solution for the determination of the borderline. Of course, we can perceive that this is not a good solution, because it doesn't really separate the red from the blue. So in this case, we need to have another try. So we can draw another green line, as this case indicates. And again, we project all the red dots and all the blue dots onto the green line. And in this case, we do see a perfect separation of the red from the blue dots. And in this case, we can simply determine the middle points on the green line, right? So these middle points, and starting from this middle point, we can easily draw a vertical line, vertical to the green line, but pass through that middle position. That vertical line is the borderline that separates the red from the blue. So this is a so-called Fisher linear discriminant method for determining the borderline of this particular data set. Okay. Now the third method. Okay. This method is called the regularized linear discriminant method. Okay. In this method, we focus on the red dots and the blue dots separately. We try to draw a circle that maximally inclusive of the red dots, minimally inclusive of the blue dots. So one possible solution is illustrated here. You have a red circle here that actually include almost all red dots, but maybe with the exception of just the two blue dots. And we have a blue circle that actually includes essentially all the so it's up to how you interpret this one. So essentially, if you think it also passed through this one, then it includes all the red dots and without again, it's up to how you interpret this one, whether you count it as included or not included. So essentially, we arrive at these two circles, red circles and blue circles. Normally, there are two intersections of the two circles, and so these two intersections are 2 points in this two-dimensional space. We know that if you connect any 2 point in the two-dimensional space, you actually generate a straight line. So that straight line is the borderline that separates the red from the blue samples. So now we showed you 3 simple machine learning method. Essentially, they are all some sort of linear discriminant type of method. Okay. Now we look at a more complicated situation. We no longer remember that we are no longer interested in a straight line, but rather wish to consider more complicated lines, the borderlines. In this case, as I just mentioned, that we may look at the borderline from the perspective of the samples. Okay, we know that a borderline, a generalized borderline, should be such that it maximally covers all the, for instance, the red dots without without covering the blue dots, and all the so the negative or the blue zones uh, must be such in a similar way that the borderline should be such that it keeps all the blues together in the same zones, no matter how complicated the borderline is, without inclusive of the red dots. Okay. In this case, we can imagine that if we are in the red zone, the pink zone, right? We are the red dots in the pink zone, and we should expect that within the zones we can more easily find our red dots of the same class, our friends, rather than our oppositions, right? So this comes with the idea that if that it must be the case, then we can design an algorithm in such a way that we simply look at our neighbors, right? If we are supposed to be in the the pink zone, then our neighbors should be such that it has the more possibility to encounter red dots rather than the blue dots. So this way we introduce this so-called nearest neighbor classifier. Okay. In this simple case, for instance, we look at an unknown sample, the white dot on the upper part of the zone, right? And then we can look at the neighbors, and unfortunately, the neighbor is a blue one. Then we may assign, based on nearest neighbor classifier, we may assign the class of this white dot with the color of the nearest dot. The color of the nearest dot is blue, so in this case, it becomes blue. And then we have a second case, which is also a white dot in the light blue zone, and we look at the nearest neighbor. It's a blue dot, so we assign it as blue. So in this case, we make this kind of assignment called the nearest neighbor. But we do see a problem here. As I mentioned, that our principle is that within the zone, we should have more possibility to find our own class other than the opposition, right? And through our eyes, we can see for the white dot in the upper zone, essentially, if we look at around the neighbors, we have more opportunity to find the red dots rather than the blue dot, because there's only one blue dot, but there are multiple red dots. So this way we know that a simple nearest neighbor classifier is not essentially is not the best one, to say the least. So that's why we introduced a new method called the k nearest neighbor method. And it's frequently called the KNN, k nearest neighbor method. In this case, we not only look at the nearest neighbor, which correspond to k equals to 1. K here refers to an integer number, okay? So we can consider the case of k equals to 3. You can see the figure on the right-hand side. If we consider k equals 3, that means if we look at the 3 neighbors, we can see that we have more opportunity to find the green ones rather than the red star. In this case, we should assign the sample with the question mark as the green one rather than as the red one. Or else we could consider k equals to 7 case. So in this case, we can see that we have more red stars than the green ones. We have more opportunity to meet with the red stars. So that means we should assign the question mark, the sample as a red star. So we can see that with different k values, we may arrive at different answers. So the question is, what is the right answer? That is up to the training process, because we do have a lot of data to train KNN to determine which is the best K. Okay, now let me pause here for you to think about this question. I mentioned that we have this K nearest neighbor method with K being an integer number. I talk about k equal to 1, 3, and 7. So my question is, can we take a k as an even number? That means k equals 2, equals to 2, equals to 4, or 6. Do you think we can take a k as an even number? Do you have an answer? Okay, because this is not we are not in the same lecture room, so maybe so I just give you the answer. So typically we cannot take a even number for k. The reason is that if that is the case, if k is equal to an even number, we may frequently encounter a situation that our k neighbors are of equal number. For instance, if we take a k as 4, we may have 2 red stars and 2 green triangles. In this case, we have some kind of Hahn decision, right? So that means indecision. So we should not put ourselves in that situation. So that means that typically we always choose k as a odd number. 1, 3, 5, 7, 11, 9, and so on and so forth. So these are the cases. Okay. Now we look at the third method. So this method is somehow complicated. It's a good illustration of how statistical thinking can come into play. So in order to explain the statistics thinking, we visually look at this example. Again, we look at the distribution of the red dots and the blue dots. Okay, so so the question is, how do we determine the borderline between the red dots and the blue dots? Okay, so we notice that in some regions there are a dense distribution of red dots. There are some other regions that there are dense distributions of blue dots. We can be very certain that if we encounter a dense distribution of a certain color, that must belong to that color, right? So this gives us an idea. Why not we look at the density of the samples based on the densities to determine the borderlines. So the density can be very dense with high density values. Density can also be very sparse with very low values. That is no problem. Okay. So the good thing about the density is that so with the density function, the higher the density is, the higher the density value is. So essentially, we can visualize the density value as some kind of height, as if we are drawing the distribution of the our is essentially geological distribution of certain local region. You have mountains, you have some plain, some lower fields, right? In this situation. So if we have this concept of mountains and also the gulf between the mountains, and we can imagine that we can color the mountains. Some mountains may be red colored, some mountains may be blue colored, and the borderline should be in the gulf between the mountains, right? So this is the idea of the statistical thinking. That means we use the statistical function, right, to actually help us to determine the borderline. So it sounds very, very promising. The borderline can be of any shape. It's somehow similar to the KN I just mentioned, right? The borderline for KN can also be any of any type, because we can simply look at the gulf between the mountains to determine this kind of borderlines. But we pause a moment. Let us think about that. We assume that this kind of density distribution function, right? And if we can visualize the dots, we can imagine what the function should be. That means we have certain region, they belong to the higher ground, higher height. There are certain regions, they are the lowland regions, right? That is no problem. And then once we know the heights, we can determine the lower points, the gulf, and then we can determine the borderline. But that is under the assumption that we can visualize those dots. What if we can't visualize those dots, the distribution of the vectors in a high dimensional space? What if that's the case? So this way, a mathematician comes in, Bayes, and he designed a very, essentially invented a very powerful mathematical method, statistical method that can help us to be able to generate the kind of density function for us. That means we must have a method to generate the density function before we can really apply the Bayesian classifier method. So that's the main topic of today. How can we generate a density function based on the Bayesian probability distribution methodology? So we begin with an example of coin tossing, right? And so we have this question: when we toss a coin, there's always a question of what face it is on the top when it actually fall on the ground. So that's always this question: what is the probability to have the head on top? So that is the question. Based on the Bayes, actually, we do have a knowledge about the probability distribution. That means, of course, we all know the answer. So the heights on top the probability of the heads on top is 50%. It's 50% the case. So because of the so-called normal distribution pattern of the probability of one being on top against the other. Okay, so for this coin case, we may be able to determine because we know it is even probability. So you can have this normal distribution type of function. But what about a general complicated distribution case? Can we generate such a probability function for us? Okay, so we are going to look at it. First, we look at the natural phenomena or human activity phenomena. All these phenomena, you notice that they follow some kind of statistical pattern called the prior distribution. Prior means that they actually follow predetermined, predefined, or predetermined knowledge of certain distribution. In this particular example, we are talking about the cancer incidence of human being with respect to age, from very young age to very old age. You can see that as the age goes older and older, you do see a rise of the cancer incidence. It tops around 65 to 69 years, and then it begins to drop. Okay. Now, my second question of today, why is that when we go beyond 70 years old, why the cancer incidence actually drops rather than further increase? After all, the older the health condition should be weaker. So you expect more cancer case. Do you have the answer? It's because of the population size decreases as we go beyond 70 years old, and more people actually passed away for certain reasons, disease and some other problems and so on and so forth. So the population, so actually a very low percentage of people can live much beyond 85 years old. So that's the reason you see a drop rather than a further increase. Okay, that's the case, the distribution of cancer. We see that this distribution actually follows by a similar distribution. That means incidence increase to a certain age and then decrease. This pattern actually follows in many different diseases, as this figure illustrates. You can see different color represents different disease. They all follow. Of course, so the general trend is the same, but the exact shape can be different. Okay, so it is we later on we will discuss how we can not only to generate a statistical distribution function for a general trend, but also for specific shape. There's a means to do that. But here we just look at the examples of the existence of so-called prior distribution. That means certain natural phenomena, certain the human activity phenomena, they all follow fixed, predetermined statistical pattern that can be easily modeled by a statistical density function or distribution function. Okay, so now we look at a second set of examples. This is about some very essential nutrients or essential molecules inside our human body, like NAD plus. So NAD plus is essential for maintaining the health of our conditions like the metallic process, DNA repair, and so on and so forth. These are all important in dealing with the aging problems. But unfortunately, NAD plus actually decline with aging, as this figure shows. You can see the declining curve of the NAD plus. Okay, now we look at another essential element of our human body. A special type of stem cells. Okay, this type of stem cells, you see, it also decrease with age. It follows this kind of essentially it's more like an exponential decline curve, very similar to the NAD. So it's the same trend. But of course, the declining rate may be different, but the trend is always the same. And another set of example is the hormones. You can see it first increases and then it decreases, even though the hormone pattern of male is different from female, but it only different in the specific shape, but the general trend is always the same. Increase first and then decline after certain age. Okay, this kind of pattern also occurs in our bone density. Also increase first and then decrease. So you can see the trend. Okay, and this is also the collagen in our skin. Collagen being a protein, very important for maintaining the health condition of our skin, retaining fresh water, countering the radiation damage, protection from other disease problems. Unfortunately, you see it is almost a linear declining the pattern of the collagen. Okay, about our humans' activity, economic activity, you see this is the pattern of the GDP, annual GDP of the US, and also the variation of the GDP. You can see both. And then this is the US, and then this is the Japan. You see, even though the detailed fluctuation may be different, but the general trend is the same. Of course, this raises a question: can we generate a statistical distribution function or density function that not only can account the specific shape, but also can account of this kind of specific fluctuation pattern? I can tell you the answer is yes. We are going to look at the how we do that later on. Okay. So this is an example of Singapore. You can see it is always the same trend. Only difference is the slightly different patterns. Okay, and then this is the GDP of China. So no matter what the country, you can look at the GDP of your own country. I'm sure it is more or less a similar trend. After all our countries actually grow, so actually develop more and more advanced. After all our peoples actually make a lot of effort to actually contribute to the society, contribute to the economy, to make our life better. So we are bound to grow further and further. So that's the intrinsic driving force to give us this kind of distribution. Of course, if we look at the biology, if we look at the medicine, there are also some intrinsic driving force that make the pattern happen. Okay. Now the question, how can we generate a statistical function to cover all those, a general pattern, a specific pattern, a specific fluctuation. Okay. So we begin with very simple distribution. Of course, it's simple in the sense of statistics, but if you look at the function here, it's already quite complicated. So unfortunately, this is the nature of statistical theory. It comes with very complicated mathematical algorithm, mathematical function, even though statistical distribution-wise, it may be simple. In this case, I can tell you the complex function I just show you actually generate this kind of distribution called a normal distribution. Normal being that it is symmetric around the central point. This is the central point, right? And then you can see that it is the top, and that means it has the highest probability of happening or highest density in this particular point, and then the density drops as it goes both ways, either this way or that way, and then eventually it drops to almost zero. You see a perfect distribution, a symmetric distribution around this central point. So this is called a normal distribution. So that normal distribution is determined by this function. It's called a beta function, or we can call it a beta prior. A prior, as I defined, as I mentioned, is a definition of a pre-knowledge the distribution function or predefined function, which is this normal function. Of course, if you notice this, you do see some parameters like parameter theta and there's also other parameters. We look at the theta with different theta values. You can see it generates different height, different width of the normal distribution. So we can see that we do have some parameters to control the general shape of this distribution function. Okay. Okay, so that's the simplest foundation type of distribution. Okay, now we look at the coin toss experiment. We look at this video, right? So what's the happening of head on top or the other on top? So this is the real case. Okay, now we make things more complicated. What if we no longer have a normal distribution, symmetric type of distribution? In this case, we introduce more complex statistical function to describe a distribution that is different from normal distribution. So this is an example of binomial distribution function. Binomial means that it's no longer have one normal symmetric type distribution, but it's a composition, it's a combination of two normal distributions of different shapes, as the example here shows. So we have a blue normal distribution, we have a red normal distribution, and then we combine them together to form more and more complicated distribution function. So this way, and then we can make even more complex to generate with three normal distributions, combine them together. Now we can show you an example how the three combined combination look like. So it's these kind of things. Okay, so you simply stack these three together, it gives you, sorry, actually it is a two combination, a blue and the red one. So the black one is not a third distribution. Sorry, actually, I made it wrong. The black one is the combination of blue and red distribution function. So we look at the video again. We can see how the black one changes with a different type of combination of blue and the red ones. Okay, we will repeat again. It's kind of somehow stuck. Okay, and you can see we keep the blue normal distribution fixed, and then we increase the height, the shape of the red one, and then you do see the change of the blue one. Okay, and then also the change the black one, and you do see that the black one is actually no longer a perfect symmetric one, but rather it's a slightly asymmetrical one. Okay, now the next question is how can we make it a very abnormal type of shape and even add the essentially the noisy distribution, the fluctuations. In this case, we have to introduce so-called Markov chain Monte Carlo, because after all, the Monte Carlo method actually adds the noise, adds the fluctuation into the statistical distribution. Okay, so here is an example of we adding the random noise. So what happens if we add the random noise? You can see that by adding the noise, as the perfect normal distribution becomes essentially blurred into the shape you can see on the essentially on the left side. Let me replay it again. It's okay. Somehow. Okay, we see it again. Okay, this kind of statistical noise or the fluctuation is actually fluctuating around the middle point. If you notice that, maybe I play it again. Right? It fluctuates around the middle point. So it's kind of almost like a symmetric fluctuation. What if the fluctuation becomes asymmetric? Of course, we can do that. I can show you in the next example. So in this case, actually, we simply what so far I showed you that we can combine different normal statistical functions to make the change of the shape of the distribution function. We can add a Monte Carlo noise to make the shape becomes irregular shape, right? Now we want to make it even more irregular, more essentially more asymmetric. What can we do that is that we can actually change the fluctuation center points, as I show you here. You can see that you can, so in this case, we lift the fluctuation middle point, and then we lower the fluctuation middle point. You can see by doing that, we actually generate a highly irregular shape of the distribution function on the left-hand side. Let me show you it again. So this is called the Markov chain Monte Carlo. So the previous one is simply Monte Carlo. Now we have this Markov chain Monte Carlo to allow the center point of the fluctuation to move along a certain essentially along a certain certain function essentially. Now we look at the statistics again. So essentially, we are able to use the combination of normal distributions, use Monte Carlo, use essentially the different fluctuation functions to generate many different kind of distribution function or density functions, irregular type of density functions. So now density function becomes multiple types with different p functions, probability functions, and then so that's why you can see here you have a multiplication of multiple probability function or density functions to essentially to represent any kind of distribution of real data. And then based on the multiplication of these density functions, we can easily define the borderline. So this way. So this is the example of you can see the density functions, and then you can see that how you can define the borderlines to separate in this case, we have three colored ones. So the black one, the green one, and then essentially green blue ones. So you can see the borderline is simply in the gulf between the mountains. Okay. So this is the essentially the lecture. Let me see how much time we have. Whether we can have time. I guess we have time to actually talk a little more about the next. So before that, maybe let me ask you if you have any questions. So actually from today, we actually talk more about the technical details of machine learning method. So I don't know how easy or how difficult to actually digest these contents. Okay. So I would like to hear about your feedback, your questions. You have any questions?
Okay, thank you very much, Professor Chen. So let me take questions from the in-person audience. Any questions for Professor Chen for today's lecture? Okay, so there is a question in the chat box, sir, for you. There is a participant with the name Sana Nawaz. She's asking, can you please describe what is prior distribution?
Prior distribution means it is a pre-knowledge distribution. It could be the distribution we already know, or it could refer to the distribution we can know. That must be in existence, either in nature or in social activities or whatever. So that's called a prior distribution. Okay. So if any phenomenon has a prior distribution, that means we can find a better way, particularly statistical method, to model it more efficiently. Because if we know there's a prior distribution, there must be some kind of set function that can actually represent it. So the question is, how can we find the representation? Bayes actually taught us that you can use the combination of normal distribution functions. You can add noises, add fluctuation. You can actually add moving fluctuations to generate any kind of prior functions. By adding each probability function, you add certain parameters. Essentially, you just scan those parameters, and then you can train AI to find those parameters in order to determine the statistical function. Once statistical functions are determined, the Bayesian model is very useful because it actually grabs the knowledge from the reality, right? And then you should be able to utilize a Bayesian model to predict certain things for you.
Okay, thank you very much, Professor. So there is another question from Mr. Muhammad Ahmed Hafiz. He's asking, does Bayesian probability functions occur in 3D to be analyzed?
Bayesian functions, so you can generalize that, of course, because normally our distribution is in high dimensional space, so it must be in high dimension. But we cannot visualize that. So for visual illustration purpose, we only show you low dimensional distribution. But in reality, when we do machine learning, normally it is in a very high dimensional space.
Okay, thank you very much. So there is another
Okay.
question. Is there any limitation to use Monte Carlo simulation in biomedical AI?
Monte Carlo, so again, it depends on how. So Monte Carlo is a intelligent way to avoid because if you generate a kind of fluctuation, generate some kind of noise into a system, there's always this question, and what kind of noise level in what kind of distribution. Normally you have multiple tries, right? Essentially, mathematically, it means that you have to try different random numbers, different type of shape, height, and so on, width, and so on and so forth, those kind of things. It's so complicated because particularly in high dimensional space, particularly if you have multiple statistical, you have so many normal distribution functions to begin with, and the parameter space is very large. Monte Carlo method is an intelligent way to search the parameter space to help you to reduce the number of tries in some sense. The theory starts from the bet theory, right? If you want to win a bet, and you always have to determine the chance. Of course, you don't want to try too many chances to lose too many things. So it comes with this kind of theory. So again, it depends on sometimes it's very hard to say. It depends on the data type, depends on a lot of things.
Okay, so there is another question from Ms. Amna Dilshad. She's asking, do simple supervised models like nearest and Fisher method still have practical value in biomedical application, or are they mostly replaced by deep learning?
If you have more data, definitely you go for deep learning. But you don't have enough data. Sometimes can actually works. It still you can still see some paper actually employ KNN to do some kind of classification. Of course, it's generally rare to use KNN. For instance, so normally you do have certain at least dozens of data, right? If that's the case, you may try, for instance, random forest some other methods that actually are more sophisticated. So these are the topics of our next lecture to talk about more sophisticated machine learning methods. Okay. But
Okay.
you can't discount, you can't simply throw away can. Sometimes you may still use that. So we asked by, so we published a paper. So let me give an example. We published a paper in Nature Machine Intelligence in 2021. So in that paper, we introduced a new deep learning method uh, for screening pharmaceutical properties. So the referee asked a very simple question. So actually, our idea is that we formulate the representation, molecular representation, molecular features, rather than hard working at the improvement of the AI algorithm architecture. So we formulated the molecular feature in such a way that we want to make the feature more from a irregular distribution to a more regular distribution. Meaning that we make them more like a image rather than a random distribution type of data. Random distribution means that, for instance, if we look at molecular properties, essentially these are the physical chemical properties like molecular weight, like whether it is hydrophobic, meaning that whether it dislikes water or not, right? And then there are some other chemical properties and also other physical properties of each molecule. Then there's this question, right? So if you want to generate a vector for the molecular properties, you have to position molecular weight somewhere, position the hydrophobic property somewhere, other chemical and physical properties somewhere, right? So that means which property you position first, which you position second. If you position incorrectly, essentially you randomize that. Just you can do it yourself. You choose any image. They are composed of pixels, right? If you randomize the images, you can search the internet, randomize the image of a certain image, randomize the pixels of an image. You can see essentially you just see a noise, a figure of noise without recognizing anything. Now you imagine that if you position these properties without making them regularly distributed, you there's more chance that you essentially you randomize that. So the question is, which molecular property you put first, which second? You can think about this problem. You immediately realize there must be a serious problem here. So we solve that problem by using, again, using a very sophisticated method developed in differential geometry. So essentially, we have to deal with this high dimensional, randomly distributed high dimensional data using using a geometrical method that is capable of dealing with high dimensional distribution, high dimensional space. We use this method to make the data more regularly distributed. So this is a sophisticated deep learning method. Then the referee asks this question, okay, if you can make the data regularly distributed, what if you use KNN, use your molecular feature, put the input the feature into KNN? What happens? Uh, what is the performance of the KNN if you use your feature, your molecular feature input into KN. So we answered this question by by generating KN model for all the data sets. And surprisingly, there are a few, I think two, if I remember correctly. There are two cases actually KNN models outperform all the other models, including our own sophisticated deep learning model, including other people's sophisticated deep learning model, because by that time in 2021, the state-of-art deep learning method is called the graph-based deep learning method, graph CNN models. So actually, there are two data sets. A simple model can actually outperform all those sophisticated models. So that means that you can't really count the simply throw away KN, because in some cases, particularly if you have a low number of data, KN may actually help you rather than being some kind of non-contributing method. Okay.
Okay, thank you very much, Professor Chen.
You're
Due to time
welcome.
constraints, we are not able to take all the questions.
Okay,
Uh,
so
And with this, we come to end of lecture number 3 of this series,
okay.
course series. We will resume our lecture number 4 on Monday.
Okay, on
There-
Monday. Okay.
Yes, there is no activity or a lecture in person or online on weekend, that is Saturday and Sunday. So we will gather here on Monday, the coming Monday, that is 28th of July, and at 1:30 Pakistan time, 1:30 p.m. Pakistan time.
Okay, yeah.
Yes, and as already shared with you, attendance is mandatory at least for 80% to get the certificate for this course, because this is a course that is designed in 19 different lectures. So you have to attend either in person or online 16 of these lectures to qualify for the course. And I was also seeing that in the chat box, there were some people saying that there has to be some real world data sets where people can practice, and also if there will be lectures on the practicability or application of AI or machine learning in the real life applications. So if you go to our website and you see the course content in the lectures at the end of the series, Professor Chen will be covering those practical applications. So first of all, he's just building the foundation, and then we will move on to the practical applications. And with this, let us all thank Professor Dr. Chen for his lecture for today.
Okay,
And
before we end, let me add that regarding to the practical sessions, we are going to have a actually Dr. Wang to actually give the illustration of the practical practice of AI code starting from the 5th lecture.
exactly.
Because we have to learn some fundamental things before we can give you the lectures. But you have to bear that Dr. Wang actually he is not good at English. So sometimes he think about how he can actually better deliver the practice to you, and then so we already made some suggestions. Maybe let him to practice more, or he can find some online tools to illustrate that. Essentially, we wish that you so we suggest you to so from the 5th lecture, maybe every 2 or 3 lectures we are going to do a practical session. In practical sessions, it's better you bring your own computer, and then you are supposed to follow the illustration. You download the code, and then you essentially install the code and try to make it running. So that is the bottom line. And then each code may require certain data. So either the data is actually attached together with the code, or that's another source for you to get it. So this way, you will be able to do essentially a real life practice. So in reality, this is all our students actually have to go through if we need them to do a project and they need to get the code and then if necessary they have to modify the code to make it more suitable for particular use. But of course we don't require you to modify the code, but we do give you the opportunity. We do encourage you to actually learn how to download the code, install the code, and make it running. So that's the bottom line. Of course, after you make it running, you can actually practice, follow some, because each code, they normally give you some links or some, or even some examples how the code has been applied to in certain papers for solving certain problems. And you can do the same thing, and this way is the best way to learn. Of course, it's also a lecture is just a lecture. Without practice, you can't really do the real thing. Just like if you just learn swimming without really practice swimming, you can never really comprehend the swimming. So I do encourage you to actually do the real practice. Okay, thank you.
Thank you, Professor Chen. So I hope that to summarize what Professor Chen said, that from lecture number 5, which will be on Tuesday, there will be some practice of downloading and installing and running the code on your respective laptops. And this will be facilitated by Professor Dr. Wang, who will act as a technical facilitator. Professor Chen, will you email me any file so that we can distribute to our participants for the code, or would it be online?
Dr. Wang will contact you. Okay.
Okay.
So I
Okay.
think he has already had the WeChat linked to you, right?
Okay. So maybe we can connect with him. You can connect me with him
Okay,
through WeChat.
I forward
Yeah.
your WeChat to
Yes.
him.
Yes.
Okay.
Thank you.
Okay.
Thank you.
Okay.
And
Okay.
also,
Thank you.
Professor Chen, I have sent you a modified module for the program, for the course, because,
Okay.
there
Okay.
are 4 days which are excluded
Yes.
because of the weekend. So you can see if the new dates, they suit
Okay.
you. And
Okay.
if
Thank
not, you
you.
can suggest alternate dates. Thank you so much.
Okay. Okay.
Okay,
Thank
thank
you.
you very much to
Okay.
online
Thank you.
participants, and
Okay.
thank you very much for the in-person participants.